Measurement of the work function. The work function of a material is examined using the apparatus shown schematically in the figure. The ammeter measures the photocurrent. So we have an ammeter here that measures the photocurrent. The voltage of the anode relative to the cathode is VAC. So this is our cathode. We have light incident on the cathode, electrons are ejected, so cathode gets positively charged. Anode is basically getting negatively charged, so we have electrons flowing towards the anode, and we have the voltage anode with respect to cathode, VAC. Part A, the switch is in position B while radiation with wavelength 140 nanometers is incident on the cathode. So the switch is in position B. We're applying minus 15 volts here between these two terminals. And we have a 1 kilo ohm and a potentiometer here. It is set at 3.2 kilo ohms and there is no photocurrent. So we don't measure any photocurrent here. What is the potential difference? VAC. Okay. So in the equivalent circuit here, we have 1 kilo ohms. The potentiometer was set at 3.2 kilo ohms. There is no current flowing here. So if you don't have a photocurrent flowing here, that means there is no current flowing on this branch either. So we have this equivalent circuit. And this is our anode and this is our cathode terminal. So we want to know the potential difference VAC. Okay, and basically you can observe from this equivalent circuit that we have a simple voltage divider. This is a simple voltage divider. So for example, if you apply Kirchhoff's voltage law, KVL, you would see that you have this current I flowing in this loop here. So we have current flowing from plus to minus. I times 1K is the voltage drop. I times 3.2K is the voltage drop. Minus 15. Going back here, we have basically completed the loop. So this is basically following this loop here, starting from this point and ending at this point. So you can see that we have I times 1K voltage drop, and then we have I times 3.2K, and then we have, so we have plus minus plus minus 15 volts here is equal to 0. So the potential difference between this point and this point when I complete the loop should be 0. So this gives me a current I 15 divided by 4.2 kilo ohms, and that gives me for the potential difference VCA 3.2 kilo ohms times the current I, and this is going to be 3.2 kilo ohms, 3.2K times 15 volts divided by 4.2 kilo ohms. So K's will cancel here, we don't have kilo ohms. And if you calculate the potential difference of the anode with respect to cathode, this is minus the potential difference cathode with respect to anode, and this turns out to be minus 11.4 volts. Does it make sense that we have no photocurrent here? The anode is at a negative potential with respect to the cathode by minus 11.4 volts. That means these electrons will get decelerated. So we have a negative potential here. So the electrons will will be decelerating as they go from the cathode to the anode, and we won't have a photocurrent. So that basically makes perfect sense for this scenario. Now, in part B, the resistance R is slowly adjusted to lower values until the first hint of a photocurrent is detected in the ammeter. That happens when the resistance is 334 ohms. What is the value of VAC at that point? Okay, now we have readjusted this potentiometer to 334 ohms, and once again we're looking at the anode to cathode potential difference, and this is at the onset of photocurrent. So what does that mean? Basically, that means we have a stopping potential applied. So that's what really means. Okay, so again, using our voltage divider, simple voltage divider circuit here, we can see that voltage of the cathode with respect to the anode is basically 334 resistance times the current, which is 15 volts divided by the total resistance, 1334. So it is going to be 3.76 volts, which gives us, for the potential of the anode with respect to the cathode, minus 3.76 volts. So basically this gives us our stopping potential. Therefore, our stopping potential, delta Vs, is 3.76 volts. But the answer is minus 3.76 volts for voltage of the anode with respect to the cathode in this scenario. So that's the onset of photocurrent. That means I just have a negligible current flowing here. So basically the equivalent circuit did not change because I have just started observing a current. It's a very small current, so I can neglect it, and this gives me the potential right at that point in time. Part C, what is the work function of the cathode material? So this allowed me to evaluate the stopping potential now. Now I can calculate the maximum kinetic energy of the photoelectrons will be equal to the amount of energy provided by a photon, HF, for the one photon, one electron process. HF minus the work function will be equal to the stopping potential energy. So this phi work function is then HF minus E delta Vs. So that is equal to Hc over lambda minus E delta Vs. And for Hc over lambda, I have a shortcut, 1240 electron volts nanometers. The wavelength of light is 140 nanometers minus 3.76 electron volts. So these nanometers cancel, so I'm left with electron volts here. So this gives me the work function phi to be 5.1 electron volts for this electrode. So since I know the stopping potential from this part, I can use the energy conservation. The stopping potential energy is equal to the maximum kinetic energy of the electrons, which is the photon energy minus the work function. Part D, the switch is then thrown to position A and the ammeter measures a photocurrent of 3.71 milliamps. What is the current I in this case? Okay, so we have a photocurrent 3.71 milliamps being measured here. We want to know the current flowing in the potentiometer branch. So this photocurrent is basically flowing down on at the left side, and here we can use Kirchhoff Voltage Law, but we have to be careful. Here this was minus plus 15 volts. Now it's plus minus 15 volts. Okay. So what I'm going to do is apply Kirchhoff Current Law Kirchhoff Current Law at the node N. Okay, so that means all the currents that are entering this node should be equal to 0. So who is entering? I15, the current of the 15 volt branch is entering, and these two are leaving. So in this convention, so I15, the current that enters, must be equal to the current that leaves, current I plus the photocurrent. And if I do Kirchhoff Voltage Law, KVL, this is KCL. If I do Kirchhoff Voltage Law for this loop here, you can see that I have, if you follow the current, this is plus minus, this is basically I15 flowing here plus minus. So if I write the total potential starting from this point N and ending at this point N, this will be I times 334 ohms plus, so these two currents are adding up. I plus IP is I15, so that's the total current that flows here. I plus IP times 1K, and then I have plus minus minus 15 volts here. So I see the minus on this side. Minus 15 is equal to 0. So I have 1334 I plus the photocurrent times IP times 1K is equal to 15 volts. And the photocurrent was given to me as 3.71 milliamps. Therefore, I can calculate the current I to be 15 minus 3.71 multiplied milliamps multiplied with 1K, so they will cancel. I will be left with ohms. So basically, I will be left with volts here. So this will be IP 3.71 milliamps times 1K, that gives me 3.71 volts. 15 minus 3.71 divided by the resistance 1334 ohms. This gives me, for the current I that flows in this branch, to be 8.46 milliamps. So using Kirchhoff Current Law and Kirchhoff Voltage Law, I was able to calculate the current flowing in this branch. Part E, the switch is then thrown to, okay, so part E is what is the value of VAC? What is the value of VAC? Well, VAC is due to this current I flowing in this branch. So VAC, remember, this is the anode, this is the cathode, is 8.46 times 10 to minus 3 amps multiplied with the resistance using Ohm's law. I calculate the anode to cathode voltage 2.83 volts. Okay, and part F, the switch is then returned to position B, and the wavelength of light is reduced to 65 nanometers. The photocurrent increases. What is the minimum value of R for which the photocurrent will cease? Okay, now the maximum kinetic energy of the photoelectrons will be the energy provided by the photon, HF minus the work function phi, which is 1240 electron volts nanometers divided by 65 minus the work function we have found to be 5.1 electron volts. This is E times the stopping potential. Okay, so we can calculate the stopping potential energy to be 14.0 electron volts. So the potential is 14 volts basically. that's going to be equal to using the voltage divider. So I want to know the new value of the resistance here. 15 volts times R divided by R plus 1K, and 14, that's 14 volts. So 14R plus 14K is equal to 15R. So that means the resistance should be equal to 14 kilo ohms. Okay, so the switch was thrown back to position B, which means I have this equivalent circuit, but now this is R, and I know the potential difference between anode and cathode. So I use the same voltage divider. It's R times 15 over total resistance. That's the voltage appearing with respect to the that's VCA, but VCA is going to be 14 volts, so that we will have the stopping potential for energy 14 electron volts. That means V cathode with VAC would be minus 14 volts actually. So okay, in summary, we're trying to measure the work function of a material using the photoelectric effect. We have light incident on the cathode, ejecting photoelectrons that are traveling towards the anode, and for a certain potential difference VAC, we measure the onset of a photocurrent, and before that we have no photocurrent. In part A, the switch was at position B. We have minus 15 volts being applied here between these two terminals, and the wavelength of light is 140 nanometers. The potentiometer setting is given. I want to know the potential difference anode with respect to cathode. So with this equivalent circuit with no photocurrent here, we have using the Kirchhoff Voltage Law, if you assume that the current flows in this direction, starting from this node and ending at that node, we have I times 1K, I times 3.2K minus 15 is equal to 0, which gives us a current 15 over 4.2K. And the voltage cathode with respect to anode is I times 3.2K. And the voltage of anode with respect to cathode is minus of that, minus 11.4 volts. At the onset of photocurrent in part B, we were given that the resistance is 334 ohms, so we adjust the potentiometer until we see a photocurrent. At the onset, the photocurrent is negligible, so we can calculate VAC using our voltage divider again. 15 times 334 divided by the total resistance 3.76 volts is VCA. VAC is minus 3.76 volts, which gives us a stopping potential of 3.76 volts. Now what is the work function? Then work function is HF minus phi is equal to E times the stopping potential. So we now know the stopping potential is 3.76 volts. So with that we obtain Hc over lambda 1240 electron volt nanometers divided by incident wavelength 140 nanometers minus 3.76 5.1 eV. In part D, the switch is then thrown to position A, and we know the photocurrent. What is the current I? In this case, current I is the current that flows in the resistance potentiometer branch. Okay, so if you take this current I to flow in this direction, then we can use Kirchhoff Current Law at this node, which tells us that this photocurrent plus the current I is equal to I15, the current provided by the voltage source. And Kirchhoff Voltage Law tells us that if you follow this path here, I times 334, I times 1.2K minus 15 gives us 0. So this gives us a current of 8.46 milliamps if we substitute for I15, I plus IP here. So it's 8.46 milliamps for this convention, but if you look at this convention, it's actually minus 8.46 milliamps, but as long as we show our convention here, that doesn't matter. In part E, we want to know now the resulting voltage, anode to cathode voltage, that is basically I times 334, that is plus 2.83 volts. In part F, the switch is returned to position B. We want to know the minimum value of R for which the photocurrent will cease for a wavelength of 65 nanometers. The switch is thrown to position B, so we have this equivalent circuit with this potentiometer here. So the maximum kinetic energy we provide is HF minus phi. We can calculate that to be 14 electron volts. And the potential on the resistance R will be 15 times R divided by 1K plus R using the voltage divider. And that must be equal to 14 volts because we have the stopping potential. So this gives us R is equal to 14 kilo ohms.